Welcome back. In this video, we're going to go over section 5.2, which is about binomial probability distributions. So along the way, we'll review just what it is that is required for any discrete probability distribution, and then what it is that makes a binomial distribution special. And we'll see the formula for it and then some examples. So taking a look, first of all, as a reminder, for any probability distribution, there are three requirements. Number one, there's a numerical random variable x, and the values are associated. There are corresponding probabilities associated with each of those numerical outcomes. Item two, the sum of the probabilities has to be 1. And if you think back to our earlier work with probability and the OR formula specifically, the probability of one thing or another, we tend to add the probabilities together. So here, this says that we have a sum of probabilities. We add them all up and get 1. 1 is the probability of something is bound to happen, happening. And so this says basically that if you total all the possible outcomes, you have to get a probability of 1 because something's going to happen. Okay, occasionally you may see 0.999 or 1.001. That's an artifact due to rounding. Okay, each of the probabilities have to be between 0 and 1, which is true for every probability. All right, so for a binomial distribution, there are 4 requirements. And the first one, the procedure has a fixed number of trials. A trial is a single observation. I'll give examples illustrating what exactly each of these 4 requirements means here in a minute. But the first thing is that each trial has a fixed number of, the procedure has a fixed number of trials. Okay, the trials have to be independent. That is, the result of one trial can't be affected by the results of an earlier trial. Each trial has to have all the outcomes classified into 2 categories. That's where the name binomial comes in. The bi part of binomial means 2. And so the 2 possible outcomes part is important. So if you're rolling a die, it probably is not going to be a binomial experiment unless you make it like, okay, I got an even number or an odd number. Okay, there's 2 possible outcomes. You have to have 2 possible outcomes for a binomial experiment. In working with binomials, it's tradition to call the 2 possibilities success and failure, even though success may not be a good thing and failure may not be a bad thing. So we may look at the probability of a tire going flat or someone catching an illness or something, where we may not normally think of an illness as being a success, but it's just the way that it's done. What is counted as a success outcome can vary. What is counted as a failure outcome can vary. And either one is not necessarily a good thing. It's just how they're labeled. Okay, the probability of success has to stay the same in all trials. All right, so let's take a look at some examples. So first of all, we're going to toss a coin 10 times. And remember, in our course, we assume that all of our coins are fair and all our dice are fair, unless we're told otherwise. We want to know the probability of getting tails exactly 6 times. So we want to know, first of all, does this meet all the different 4 requirements for a binomial experiment? Okay, so there are a fixed number of trials. Okay, we're tossing the coin 10 times. Okay, and that's it. So this meets number 1. Okay, there's a fixed number of trials, and that's it. It isn't that we're going to toss a coin a few times, and if we got tails twice in a row, then we'll stop or something. Nope, we're doing it 10 times. Okay, the trials have to be independent. If you toss the coin 3 times, none of that information is going to tell you how it's going to come out on the 4th time. Okay, the trials are independent. Okay, each trial has to have all the outcomes classified into 2 categories, heads or tails. You can here make success be, well, tails. Tails is going to be our success because that's what we're interested in. Okay, so for this problem, I would label tails as the success outcome. But there are 2 possibilities, either heads or tails. And the probability of success remains the same in all trials. So the results don't change as we do those 10 coin tosses. All right, so some examples or anti-examples that illustrate the failure of one of these 4 conditions. All right, so first one, let's say that we do an experiment where we're going to roll a die. We're going to roll it as many times as it takes for a 4 to show up. Okay, so you might roll it once and get a 4, and then you're done. You might roll the die 3 times, and then on the 4th try, a 4 shows up. You might roll it 100 times somehow, although it seems unlikely. You might roll it 100 times and get a 4 on the 101st try. But the point is that there's a variable number of tosses until that 4 shows up. So that would fail number 1, the procedure having a fixed number of trials. Okay, for number 2, a box has 12 light bulbs, and we know somehow in advance that 7 are good and 5 are bad. Okay, we're going to pick out 2 light bulbs without replacements. So you're going to pick them out and keep them out, not going to put them back, the first one back before picking out the second one. So you just go to the box of 12 bulbs, pick out 2. What's the probability that both are good? Well, here the draws are not independent because the likelihood of the second bulb selected being good is affected by whether or not the first one is good or not. Okay, because there are only 7 good bulbs in the first place. If your first one drawn was good, then the chance that the second one is good is less on the second draw. So the point is there that the trials are not independent. For number 3, suppose that a salesperson is selling extended warranties, and the possibilities are that the salesperson could sell a 1-year warranty, a 2-year warranty, or not sell a warranty at all. So there's 3 possible outcomes there, and so that's not a binomial experiment. Okay, number 4, a salesperson goes door to door trying to make appointments to sell solar installations. We want to know the probability that in visiting 25 houses, 4 appointments are set. So there may be a variety of problems there, but at the very least, it doesn't seem like the probability of success is the same in all trials. I would assume that after visiting a few homes that the person would probably get a little bit better at their sales pitch and learn what to say and what not to say, so that by the time they got later in the trip to the 25 homes, they might be more successful. This is something that occurs in situations where training is involved. If somebody has a chance to practice a skill or something, then the outcome is not going to be the same every time. All right, so you could probably say that that's probably true about number 3, about the salesperson selling extended warranties, but there were only 5 sales, so there's not that much chance for the person to improve over that time. All right, so a couple of things, moving on. One thing in real life, or realistically, sampling is often done without replacement, which introduces dependent events. So if you're going to go and take a poll of people coming out of the grocery store and ask them, okay, do they prefer butter or margarine or something? When you're polling these people, it's unlikely that you're going to get the same person twice, right? They've left the store, they're not going to go back in and buy something else. So the sampling there is without replacement. So that introduces dependent events and makes it so that it's not technically a binomial experiment. Independence was one of the requirements. But the thing is that usually the number of participants is so large that the difference between treating it as independent and independent is relatively small. And so here, that's what this part is about, treating dependent events as independent, the 5% guideline for cumbersome calculations. And the deal is, if the calculations are cumbersome, that is difficult, and the sample size is no more than 5% of the population, we can treat the selections as independent, even if the selections are made without replacement, so that they're actually dependent. So in the case of the grocery store example that I gave, there the assumption is that the 1 or 2 people that you might poll are going to be less than 5% of the total sample size. The earlier example where we were picking 2 light bulbs out of a box of 12, there the sample size is going to be larger than 5%. So we wouldn't want to treat that as independent. All right, so what we want to work on next is developing a formula for the probability distribution. There is some labeling that goes with this, and so I want to make sure that that's all clear before we develop the formula. So the 2 possibilities in our binomial formula are going to be S for success and F for failure. Those are going to be the 2 events. And here we have P of S is equal to little p. So capital P is standing for probability here, and little p is a number, just like a variable. So the first one here that you're seeing that will be P of S equals P, and that's the probability of success. Probability of success will be little p. So probability of failure will be the complement, right? 1 minus little p, and that's going to be called Q. The probability of failure will be Q. N is going to be the number of trials. So if we toss a coin 10 times, it's going to be 10. X, the number of successes in N tries. So let's say we toss a coin 10 times and we want to know if the chance of it coming up heads 3 times, the X would be the 3. The number of successes in N trials. Okay, and then P and Q, remember, those are the probability of success in any one trial. So if we toss a coin 3 times and want, or 10 times and want to know the probability of getting heads 3 times, the P is still 0.5. It's not the probability of getting the heads the 3 times. It's just on the one try. Okay, P of X is the probability of getting exactly X successes among the N trials. So we're going to calculate this once kind of the long way, and we'll see how to use that to develop a formula for the probability binomial distribution, and then we won't have to do it the long way anymore. All right, so suppose we're again going to toss a coin 10 times. We want to know the probability of getting tails exactly 6 times. And of course, the assumption, as always, is that our coin is fair. So let's say we're going to fake it. Okay, if we're going to fake it, we want to get tails exactly 6 times. So that means that the coin would have to come out tails 6 times, and there's a 1/2 chance of that coming out. And that has to be 6 times. So that's going to be 6 times. All right, so that will be 1/2, and that will have to occur 6 times. Our probability of success was 1/2. That has to occur 6 times. We're basically using the AND formula right there, which says you multiply together the probabilities. Okay, if it's going to come up tails exactly 6 times, then it has to come up heads the other 4 times. And we'd need that to occur 4 times. Each one has probability 1/2. And so that's going to be 1/2 raised to the 4th power. All right, so there's that. So then multiplying those together, because we'd have to get the tails outcome and the heads outcome together, both. And so we're going to multiply the probabilities together. So far it's looking like the probability of success raised to the power of how many successes there are. The probability of failure raised to the power of the number of failures we have. So the thing is, if we're going to toss the coin 10 times, there's a variety of ways that this goal that we can have could be achieved. So if we get tails exactly 6 times, it might look like that with less heads. Okay, we should have 1, 2, 3, 4, 5, 6 tails. Okay, it could look like that, and that would satisfy our requirement. Or it may be the first 2 were tails. Okay, I've switched 2, but we should still have 6 tails. So let's say that I was going to continue faking this outcome. If I was going to write down another example like this, I need to pick 6 places to put a T in, right? And then I'm going to fill out the rest with heads. So let me do that. There's 1, 2, 3, 4, 5, and I guess we'll go with 6. All right, so there's 6 places I put the T, and so then the rest have to be H's. All right, so then you're going to recognize that as out of 10 little blanks that I filled in, there were 6 that I chose to put in a T. That sounds like a combinations or permutations problem, right? Out of a whole amount of something, pick some, either combinations or permutations. Next question is, which is it? Well, do you remember which T I wrote first? Does it matter? It doesn't matter. The outcome is the same, which ones are T's and which ones are H's. So that means that it's combinations. So out of the total of 10 coins, we're going to pick 6 to draw the T's in. And so we're going to multiply that multiply our probabilities, and that will give us our final answer. We don't have to have another factor in here about the heads, because once we've determined what the tails are, the heads are determined, and there's only one way to do that. All right, so it's going to look like a combinations multiplied by a product of probabilities raised to a power. So then our formula looks like this. Okay, so this first piece, color that so we can see it. This first piece is just going to be, they've expanded it in our book. So this is the combinations formula out of n total things. We're picking out x. And then we multiply that by the probability of success. That's p raised to the x power. And then q, that's our probability of failure, raised to the n minus x power. Remember that if there are n total tries and there are n total tries and x are successes, then n minus x would have to be the number of failures. All right, so that is how our formula works. So let's try it once on here. Here it says a die is rolled 20 times. We want to know the probability of getting a 5 exactly 2 times. Okay, so following our formula, we're rolling a die 20 times. So C, 20, and then we wanted 2 successes. So that's our X. The probability of success, we wanted a probability of getting a 5. Well, there's a 1 in 6 chance of rolling a 5. That has to occur twice. And then failure would be the rest of the time. That's the other 5/6 chance. And that will occur the other 18 times. Okay, so let's put that out. Give me a second to do that. All right, so going through the calculations, we end up with a probability being about 0.1982. So make sure that you're able to get that out of your calculator, and if you have trouble with that, let me know. We're going to do some additional examples, but I also wanted to show you how to do this using StatCrunch and Excel. There's a formula for this in Excel, if you're interested, and the function name for that is binom.dist, which stands for binomial distribution, of course. This function takes a couple of inputs or arguments. The first one, it says number underscore s. That's the number of successes in n trials. That would be like our x. And then the second input is the n, the total number of trials. And then the third item is the probability, which is going to be 1/6 in our case for the die one we just finished. And then something new in here is cumulative, and that is either true or false. That's when they say it's a logical value. It means that it's binary or true or false. And this says, is it cumulative? And what that says is if it's true, then this function will turn the cumulative distribution function, which is the probability that there are at most that many successes. So like in here, what if I wanted to know if it was at most 2 times in our previous example with the die? If it was less than or equal to 2, then I would have made it true here. For Excel then, if we wanted to do this example using Excel, we'll say binom.dist. And then the number of successes we're looking for here was 2. And then there were 20 total trials. Our probability of success is 1/6. And then here we didn't want cumulative, so we could just write the word false, and Excel will figure that out. Okay, so I'm going to do an example next actually using Excel. So let me show you that. All right, so here we are in Excel. If you want to try this in Google Sheets or some other spreadsheet, you can. I've never used Google Sheets, couldn't tell you on that. But in Excel, it goes like this. We're going to do the same die problem. We want to know the probability of getting a 5 exactly 2 times. So I'm going to just do this down here. Equals to start a formula, and then binom.dist. And then left parenthesis. And one thing is nice that it's going to give us a little clue here about what it is that we're supposed to type next. Here, remember, the X comes next. So this time we wanted 2. And we're doing 20 total trials. And the probability of getting a 5 was 1/6. And for this one, we didn't want the cumulative one, so we're going to say false. And then close the parenthesis and hit enter. And there we get our 0.198239. All right, so that's how this looks using Excel. And then again, sorry about the stretch there. That's how the formula is going to look for this one. 2, the X comes first. 20, the total number of trials, comes second. Probability of success is third, and then false if you don't want that cumulative distribution. All right, so we're going to work through just 3 more examples. This first one we will do one more by hand. So it says a fair coin is tossed 3 times total. We want to find the probability of getting exactly 2 heads. So out of the 3 total trials, we're looking for 2 successes. The probability of success is going to be 1/2. The probability of getting heads, which was the success outcome, there's 1/2. We're looking for that to occur 2 times. The failure outcome, getting tails, that is to occur once. Okay, then let's go ahead and calculate that. That's about 0.375. So I'll leave it to you to calculate that kind of by hand using earlier methods we had, and then you can see how that goes. All right, so let's try one more. So 2, it says a survey found that 1 in 5 Americans have visited the doctor this year. If 10 people are selected, what's the probability that fewer than 4 have? So fewer than 4 would be 0, 1, 2, or 3. So we would need to find this probability a few times. So probability of X being 0, probability of 1. Sorry, I'm writing. Probability of 2, probability of 3. So for these purposes, we would need to run the formula 4 times. If we're looking for fewer than 4 people, that would be no people, 1 person, 2 people, 3 people, or 4 people. So we could use the formula 4 times, or this would be a good opportunity for us to try Excel's cumulative function. So if we're looking for this to be fewer than 4, that would be less than or equal to 3. So we would try Excel's binomial dist formula. We're looking for 3 at most out of 10 total trials. The probability of success, 1 in 5, is 20% or 0.2. So there's a 20% chance of success here. 3 people out of 10, but this time we're going to go true because we want less than or equal to 3, not just exactly 3. Okay, so let's go ahead and do that in Excel. See what we get out of it. All right, so in Excel, we'll have equals and then binomial.dist. And then this time we're doing 3 trials. Sorry, we're looking for 3 successes at most out of 10 trials. The probability of success is 0.2, and this time we went true. Okay, sorry, shrinking there. All right, so that's going to be about 0.879 for that. All right, for our last example, I wanted to see how we can do this same calculation using StatCrunch if that's your preference. So the story here is a survey found that 30% of teenage consumers get their spending money from part-time jobs. If 5 are selected, we want to know the probability that at least 3 have part-time jobs. So just so that we know how this would go in Excel first, If we're looking for at least 3, then it's not the case that it would be 2 or fewer. So that sounds like a complements problem. So we'd have equals, and then 1 minus, because we're taking a complement, binom.dist. And then we'd be looking for how many, right? It's going to be 2 out of 10. Probability of success, 30% this time. Sorry, 10 is wrong. I'm thinking of the previous example. 5 people, 5 teenagers are selected. We're looking for 2. The probability of success here is 0.3. And then it's going to be true. Okay, so the last part, the binom.dist all the way to the end piece, this would tell us the probability of getting 0 through 2. Okay, if it's not going to be 0 through 2, then it would have to be 3, 4, or 5, right? We're selecting 5. We want to know the probability that at least 3 have part-time jobs. The part that is yellow highlighted would tell us less than or equal to 2. Taking the complement is what tells us 3, 4, or 5. All right, so now let's see how we can do the same problem using StatCrunch. Find that, there's where that is. All right, so then to use StatCrunch for this, we'll go here to where it says stat, of course, and then calculators, and then binomial. So we're doing the binomial distribution. And then we have kind of this calculator. There are 2 options for it. You can either do the standard one, which we've been doing, or between. If you click on between, you can calculate the probability of your x value lying between 2 values. We're going to do standard. Okay, for this one, the n was 5. There were 5 people who were picked. The probability of success was 0.3. And we wanted the probability of, what was it, 3, 4, or 5? At least 3, right? So at least 3, down here, probability x. Let's change that to greater than or equal to, and then 3, and then push compute. Okay, so that works out to be 0.16308, and they give us a nice little histogram. Hopefully you can see that they've colored the part that is 3 or higher in red. All right, that takes us to the end of what I was planning to show you as far as section 5.2 goes. There is another half with more examples from section 5.2. In the meantime, let me know if you have any questions, and then have a great day.